And welcome back. Now today we've got some news about the SD card reader, like this module here. And I noticed in the Arduino forum there were a few queries about how to make this a little bit more reliable and indeed how to use it at all. So let's have a look at this card reader here. I'll show you where I got that from and how we connect it up to the Arduino, and ultimately how we can make it a little bit more reliable for use with some new code and a modification to the existing hardware. Sounds exciting. So let's have a look where I actually got the module from, which is over here. Now, as you can see, this is from Banggood, where I do seem to get an awful lot of stuff these days, mainly because they're a bit quicker and more reliable in delivery than other places I've used. And if you look at this price here, £1.16, which is about, what, $1.50, 60, something like that. That's a pretty good price. Now that's from the Far East. If you want it from the EU, I think the warehouse might even be in the UK, they're not saying, but anyway, £1.80. So for this device here, £1.80 shipped to your home in the UK, and I suspect if you live in the States or Australia, you can get it from their warehouses directly there as well. Obviously Australia would be coming from Hong Kong or China, wherever they're based. So that's pretty good going. Now this is a fairly standard SPI bus card reader, which means it does use a few more wires than perhaps an I2C one would use. Not that I've found one with an I2C, I haven't got one anyway. So this uses the SPI bus, and the code that we'll be using, which is standard library code, uses the standard SPI pins. It does make it rather easy. So effectively there are 4 pins we need to use. So the chip select, clock, MOSI and MISO. We'll go through all of those, and of course 2 power ones. We'll go through what all these SPI ones are for. So in all you need 6 wires, or maybe 7, but we'll come on to that. So let's see how we can connect these wires up. They are documented nicely on here. If I can bring this into close focus. There we are. So on the camera we can now see that from the top it's ground, 3.3 volts, which we're actually not using, but it does mean you could use this card on Duet or something like that. +5, chip select, MOSI, clock, MISO and ground. Again, this is 2 grounds in fact. This last one I'm not actually using. So the standard SPI bus requires the chip select, although that can be on a different pin actually rather than the standard one. The standard one is pin 10. You can use any one as long as you tell the library that that's what you're using, but unfortunately it doesn't actually free up pin 10 then. You still have to set pin 10 high to make the library work, so you haven't really gained much. So what else? You've got the MOSI, master out, slave in, and the MISO is the master in, slave out of course, and the clock. That's the pulses by which this is reading data. Very fast pulses I might add. I think it's 100 kilohertz by standard. Can't swear to that. If I find out, I'll put it up on the video over this. So we connect these into the standard SPI pins on your Arduino or Arduino clone, and that is pins 13 down to 10, 10 being chip select. So let's have a look at the code, it will probably make it clearer. So let me just move this one out of the way. So here we have a fairly standard code example to write to the SD card. I've not actually done a read, because reading, if you've done this, reading is going to be even easier. So let's see how we might use this as a writer, because you might be wanting to log data, for example in a greenhouse, a beehive, who knows, somewhere down the bottom of your garden. So you really do want it to be consistent and reliable. So let's see how we can do that. So let's look at the code here. First of all, we need 2 libraries. One's the SD, which is standard, comes with your Arduino board, nothing to install, or is there? Come on to that. The SPI library, of course, because we're communicating with SPI. We'll skip over this one here. Oh yes, I'm just using a data pin here from one of the analog ports, just to give me some sort of random fluctuating noise value, pretending that's the data we're logging. At least it changes second by second just from the general noise, the electrical noise that there is on this card. Here I've got a pseudo sort of timestamp, log message stamp, call it what you want, just to show you that you've got a different message every second. So it's just an incremental counter. Now the first thing we must do, once we've established our serial monitor, which is only used for debugging mode, so we can see stuff on the debugging window here, the serial monitor window. We'll forget that, we'll come back to that. This is the first bit. We say, can we establish communication using SPI and the library? If it can't find it, then it gives you an error message. If it does find it and establishes communication okay, it will give you that in the debugging window. We then read a value from the analog pin, some random fluctuating value, usually around the 200 mark. And assuming that we have got a card, we'll come on to this enhancement that I'll put in here a bit later. We're going to say we're opening up a file for write mode. Now this is not totally accurate. File write actually means append mode. And if the file isn't there, then it will create it from scratch and then start writing to it, or appending to it. In that case, it makes no difference. So if we've managed to establish this file correctly on the SD card, this is the statement here, if data logged, it will return true if it worked. We just format a simple message and print it both to the debugging window and log it to the SD card. Then we close it immediately. Why do we close it immediately? Well, the data on the SD card here is presumably valuable to you. You're logging for a reason. If you were to leave the file open and just keep writing to it in a loop without closing it, and something went wrong, you'd lose everything. All the data on it would just be irretrievably lost. So by closing it after every write and reopening it, we're making sure that what was there originally is being kept every time. Every time it does a close, it flushes the buffer, makes sure the data is actually written to the SD card, and then that is at least saved. If something goes wrong after that, at least you've got the data up until that point. Then we're just incrementing the log number. As I say, this could be a date timestamp perhaps. Normally you might read it off an RTC, a real-time clock, just so you know when the data was logged. And then we just have a couple of if statements to say, well, I couldn't do that, something went wrong basically. And then for our purposes here, for the demo, we're delaying by a second and going back to the loop and starting all over again. So let's see that in action and see what we can do perhaps to enhance the whole process. So let's just plug it in. So let's just load this up now to the Arduino, compiling, and there it goes. So the first thing to notice here is that the sketch is using very nearly 15K. Now 15K for a few lines of code here just to write to an SD card is not insignificant. If you have any program that's taking up more than 15K, you're not going to be able to use this method of writing to an SD card. So just bear that in mind. Obviously if you've got a Mega or something, you're going to have much more room, or perhaps even a Wemos D1 or something like that, you're going to have plenty of room, but not for a standard Arduino or Nano or any of the variants. So let's just think about that. It's also using 48% of your dynamic memory, your SRAM. So it's not a lightweight library by any means, this. That said, you might just want a simple logging system for, I don't know, irrigation, how many bees come in and out your hive, who knows. And you could well fit the code in there. But the trouble is with using libraries, of course, is that they all use up far more space than you might think. And if you start using 2, 3, 4, 5 libraries, then you could easily run out of space on an Arduino. Your Uno anyway, and Nanos, those sort of things. Let's fire up the serial port then. Now this is uploaded, and see what we get. So there we are. Now SD card initializing completed, and these values, which are the random data values it's reading from AE0. If I touch it, look, it goes right up, and if I let go, it's very low. So there we are. It's just random data, which is pseudo data. It might be a temperature we're reading, or as I say, the number of bees coming in and out of a beehive. Who knows? So this is quietly going around the loop and writing away because it knew there was a card in here, or at least the SPI bus could communicate with this, and it was satisfied that this was all okay. So if we reset this now and take out the card, I'll do it a bit quicker than that. So if we reset this and remove the card, Now as you can see, it's once again on here come up to say it can't find the card. So we just put it back in, press reset, and off it goes. So you think, okay, this is fine, it's going around this loop now, this loop of code saying go and get me some random bit of data that we're pretending is real data that we're logging. It's saying go and open up the output file and write away the value, and if I can't write away the value, give me this error message. Now the interesting thing here is, if we make this window a little bit smaller and move this over, now what do you think is going to happen if we remove the card whilst it's writing away all this data to the SD card? Let's find out. I'll remove the actual card. There. Oh, that's a bit of a worry, isn't it? Look, 50, 51, 52. It's still writing away data, or at least it thinks it is. Obviously it isn't, because there's nothing to be written on here. I've got the thing removed. What does that mean? Well, it means of course that there's a deficiency in the standard SD library and or this bit of hardware that doesn't detect when this card has been removed. Now that could be an issue, because an operator, for example, would want to maybe retrieve the SD card and put a new one in on a daily basis, a weekly basis, who knows. So they'd take one out and put another one in, except of course what's happened is it's not detected the fact the card's been removed. And if we put this back in, you think that's fine. No, unfortunately not, because look, we're up to a line 106, 107, 108, 109, 110. We'll take it out again. Let's have a look on the computer to see exactly what's written on this card, shall we? Here's the data file since we started the entire demo, and if we go down to the bottom, look, it stopped at line 44. It never got anywhere near the 110 line we were looking at, because we removed the card from this slot and it wasn't detected. So the program continued to write away thinking it was there. Even this test here to say can I open this card didn't stop it, because, well, there's some sort of caching going on probably on this card here, this SD reader module, probably some sort of caching or something. And in fact it's known that you can't detect the presence of a card on an SPI bus. So what are we going to do about that? I mean, this could be potentially disastrous to somebody if they were logging data, weather data, the count of bees. That could be potentially disastrous. You go back after a week thinking you've been logging data and nothing's been written to the card. Well, on this particular module there is in fact a pin, and looking at it, holding it this way with the pins at the bottom and the card holder at the top, pin 5, reading from the left, is in fact a little switch, so that when you insert the card it makes that switch to ground. So the action of putting this card in, when you hear it click of course, will cause pin 5 to be shorted to ground, so that something can be detected whether this card has been inserted or not. Except on this module that pin is not connected to anything, which is an awful oversight really. They could easily have brought that pin out to one of these header pins here, but it wasn't to be. So what are we going to do? Well, ideally we'd want to solder a little wire to pin 5, which is fairly easy to do, I think, to be honest. It's not a tiny amount of soldering there. As long as you have a fine soldering iron, you can get your pin soldered to a piece of wire and bring that out to your Arduino to detect whether or not at least the card has gone in. And in true Blue Peter fashion, here's one I made earlier. So as you can see here, I've numbered them, and pin 5, as I say, starting from the top or the left hand side if it's this way round, which is not connected to anything else. I've simply soldered a piece of wire on here, brought it out to a pin so that we can detect when this is low there's an SD card in here, and when this is high there is no SD card. So at least that's one step towards finding out if there's a card in here. So let's plug this into here, that is to say unplug this one, plug this one in its place, connect this to the pin, we'll uncomment the code that's already waiting for this and see what happens. Here we are back now with the new code, which is very simple. All we're doing is saying we're including a new pin now, which is what I'm calling SD missing on pin 7, could be any digital port. And in our code we're saying if the SD missing pin, which is pin 7, is low, fine. If it's not low, there's something wrong. We set that pin, by the way, as an input pull-up, which means it has a low value only when it's shorted to ground, but by default when this SD card is out, the internal pull-up resistor brings that pin high. So let's see what happens on the serial port now. So that's saying I can't find something. Fine. We'll put it in, press reset, pretty much like we always did, and lo and behold, off it goes. Now let's see what happens when we take this SD card out of its holder. If we look at this and the serial port at the same time, look at that. It's detected it straight away because that pin now has gone high and the code detects it. On this statement here on line 41, and it says if not digital read SD missing, so it's not high, which means it can't do all this code. So what happens if we press it back in again though? Nothing. We have to do a reset. And why? Well, that's a deficiency in the original SD library as supplied with the Arduino. If we go right back to the beginning of this code, you notice we do an SD begin here. That's great. We do an SD begin, that establishes communication between the Arduino itself and this board. Unfortunately, if something goes wrong, you cannot re-establish another card, i.e. by putting a new one in or replacing it, whatever you're going to do. You can't do another SD begin because you can't do an SD.end. So Adafruit have enhanced this library and created a new version that does allow an SD.end. So let's have a look how that will change the code that we've written so far here for error detection and see how that helps us. Right, here we are with a slightly enhanced version now. Same code as before in many ways. We're still looking for a missing pin and we're reading it in from a random analog source. But because we can now do a begin and an end, what we've got at the bottom of this now is a common method to initialize the communication between the Arduino board and the SD module. And what this is saying is, if I can't find a card, display an error message and then do an SD.end. Now that allows us then to do a further SD.begin without the code falling over in a big heap. So basically it just keeps going around this loop until it can establish communication between the Arduino and the SD module. And this little routine here, this method, is called everywhere you can expect an error to exist. So initially in the setup we're calling it, we're saying init SD card, and in the main code we're saying if I couldn't do something, there was an error in reading it or an error in finding the card, it will also call that common method to say, right, something's gone wrong, let's start again as though we had a brand new card inserted. So let's see what happens when we upload this code and see what happens. Right, the code has been uploaded. Let's turn the output monitor on. So initially it says, fine, I've found the card and I'm writing away my values. Now let's see what happens when we take this card out. So far we've written to line 10. Out it comes. And it says, well, I can't find your card. It now keeps going around in this loop until it can find a card. Remember, it's executing the common routine here to say, I cannot establish communication between this board and this module, so until this card is inserted, nothing's going to happen. So let's put the card in, and now it says, ah yes, that's fine, look. And because I haven't terminated the main code loop, I just continue from where I am. So it stopped at 11, or stopped at 10 initially. Let's just stop this here. So initially it stopped at 10, gave us some error messages, but then continued from 11 onwards going forward. So if we have a look at what's on this card now on the computer, we'll see if it managed to capture all that data. So here's the data from the card, and as you can see, it went up to 10 when we pulled the card out, and then it just continued writing the data as though nothing had gone wrong, all because we had this SD.begin followed by an SD.end if things went wrong. Where's this SD.end come from then? Well, this is the enhanced Adafruit library, which I can show you how you can find that. So here on GitHub, this is the slightly enhanced library. In fact, it does say it here, slightly more friendly wrapper, fine. But this is the bit that really matters, added end function. Now this was 2 years ago from today, so it's quite a while ago, but it still hasn't found its way into the Arduino standard library. So what I've done in fact is downloaded this. You click on this button here, download zip, and what I've done actually, I've actually replaced the standard SD library within the Arduino program library, program files x86. I've deleted the SD one that came with the Arduino and placed this there in its stead, because this is effectively identical apart from a few minor improvements like that end. Now there are a couple of other SD card libraries out there. I was hoping to get the space down. If you see on this one here, look, you can still see that it's 15K just for a few lines to write some data to an SD card. That's a lot. So I've tried a couple of other libraries out, and frankly it's pretty much the same. So whether there's so much functionality in these libraries that we're not getting the code down, or whether the SPI communication to an SD module just requires that much code, I don't know. But it's certainly something to bear in mind. But I would certainly recommend the Adafruit SD library. Replace the one you got, or delete the one in your current libraries under the program files and put this one in your libraries. And it's called the same, SD, and you'll find you'll get the SD.end. So if you compile your program and it complains about that SD.end, that means you're using the very old original library from Arduino. Here's the class library for the original SD library, and as you can see, we have begin is this, make directory, open, remove directory, but no end. But with the enhancement there from Adafruit, we have now end, which allows you to issue another begin, so you're starting totally from fresh, and that is the way it should be. So that means now the code is safe, and even though we pulled the SD card at that point, this data was safe, and as soon as we could put the card back in again, it continued writing from where it left off in that main loop. So the code loop was not interrupted. I hope this was helpful, and you'll be able to implement this in just a few lines of code. Once again, if we go back to the actual code window, there are 96 lines here, well, including that last space line there, and out of all these lines there must be at least 30 lines, if not more, of comments. So really, within 20 lines of code, you've got yourself a really reliable way of writing to an SD card and allowing an operator to remove the SD card and either replace it with another one or just take it out, do some work on it and put it back in again. Sounds good to me.
That was easy.
It certainly was, and thank you for watching. I hope you're finding these videos useful and interesting. Remember, you can leave comments down below, and also click that little button that says subscribe. Okay, thanks for watching, and see you in the next video.